All right, we are going to now finish this chapter. We only have to do geometric series. We've talked about arithmetic sequences, geometric sequences, arithmetic series, and finally geometric series. Geometric series is just the sum of the terms of a geometric sequence. Here is a beautiful example for you all right here. So we can look at 1, 2, 4, 8, 16 and know that that is a geometric sequence. We add them all up. So, pretty doable. If you paid attention to arithmetic series, a lot of it is the same. Whoa, there's the formulas right there. So, you can go ahead and jot this one down. Mr. Sayers, there's two of them. Which one? Well, you choose. I end up using this one for some reason. Maybe it's because that's what I was told. What's the difference? Nothing really. You're just multiplying top and bottom by -1. So you're multiplying by a fancy 1. When you do that, you distribute that -1 to both. And that's why it changes the sign over here. I'm not a huge fan of, I just pick one and go. So totally up to you. Whoa, 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 whoa. So let's talk about where that came from. How dare I just give you a formula without telling you about that? So here it is. Let's do it. The first term of a geometric series is that. No kidding, Mr. Sayers. Well, what do you do to that to get the second term? You multiply it by r. And you multiply that one by r. So nothing too crazy. We know that's first couple terms of a geometric series. The nth term is going to be u sub 1 r to the n minus 1. So yeah, that's from our formula. That gives us the nth term that we're looking for. We're looking for the sum of the first n terms, so we know that's the nth term. What's the term right before it? Well, if we subtract an exponent or 1 from the exponent, we're kind of dividing out that r, so we get u1 r to the n minus 2. So do you see how it goes down with that power if we're going in that direction, up if we go to the right? Well, did I get it right? Yeah, I just wanted to rewrite it to make sure. Now, this is where you just have to watch. It's not like I'm asking you to come up with this, but this is just phenomenal. There's a lot of terms. First term to the nth term, all these middle terms. How are we supposed to deal with that? Last time we kind of did some combining. Let's see what happens on this one. So what we're going to do is we're going to multiply this row by r. There's the r. When I multiply every element in that row by r, I get u1r, u1r squared, u1r cubed, so forth. Everything's going to go up by one value for the r. Okay, the exponent's going to go up by 1. So n minus 2 goes up to n minus 1, and n minus 1 goes up to just n. Cool thing happens. Let's look at those two rows. We're going to subtract those rows. We're going to subtract this whole thing from this whole thing. Now watch this. So on the left is pretty obvious. I just get s sub n minus r s sub n. So that's done. But what happens when I take all of these terms minus all of these terms? Well, this is going to be taken out by that. This is going to be taken out by that. This and this are going to take out each other. This is going to be taken out by something over here. And this is going to be taken out by that. Oh my goodness, what is left? All those middle terms took each other out. We're left with u sub 1 minus u sub 1 r to the n. What was our goal? Our goal was find a formula for s sub n. And look at that, we are very close already. Now if we can just get s sub n by itself, we're just going to factor it out because it's in both terms. We get a 1 minus r. Oh yeah, the formula we just wrote down has a 1 minus r on the bottom, so let's divide both sides by 1 minus r. So there's your first version of the equation. If you factor out the u sub 1, you get that version. And if you multiply top and bottom by -1, you get that version. They all work. They all work. Like I said, for some reason, I choose that one. Glutton for punishment. I don't know. It's fun. All right, let's do our first example. You'll notice that these are a little bit more straightforward. Arithmetic and kind of how many terms are there. Here we go. So when you do a problem like this, the most important thing for any of these is it arithmetic or geometric? So it's geometric. Write down everything you know. We know the first term, we know the constant ratio, and we know the number of terms. We don't know the 12th term or the last term is 12. Be careful that you're reading that. So what do we not know? Well, we don't know what that last term is. But is u sub n part of these formulas? I don't think so. So that's kind of nice. So looks like they chose to do this one. You're just going to plug the values in. And if there's any thing that pre-calculus students plug into their calculator that mess up, the quadratic formula, that has, but for some reason, plugging in the geometric series has caused more trouble than anything. I would highly recommend, if you're plugging this in, make sure you put an extra set of parentheses around the top and put those parentheses around the bottom. If you're plugging that into your calculator, that will allow you to do the entire top and the entire bottom and then divide them. So be careful about that. There's a lot to look at there. Let's do this problem. It is a geometric series. It is in sigma notation, and I'm using the variable I instead of k. So I'm just trying to let you know that that doesn't ever have to be k at the bottom right here. It can be I, j, it can be any letter we want, as long as I'm using that in the formula here. So that's that dummy variable. I plug in that I equals, in this case, 1 into there, plug in 2, 3, 4, 5, 6, 7, get the terms, add them up. Now, since I know this is geometric, how do I know it's geometric? Because the exponent has the variable. Okay, so if the variable's in the exponent, it usually means it is geometric. Usually, because I'm sure we could figure out some examples where it doesn't work. But for you, right now, if you get a linear equation, it's probably arithmetic. If you get an exponential, it's probably geometric. All right, so if it's geometric, then what are some things that we need to write down? Everything we know, everything we know. So the first thing is you better go get that first term. So we use I equals 1 because that's where it's saying to start at. Please understand that you have to plug that in and get the term. When you plug in 1, you actually are adding 1 in this case, so you get 2. So that's squared, 9 times 2, 18. All right, so now we have our first term. We need to know the constant ratio. Well, the constant ratio will always be what is being taken to the exponent. So in this case, it is -3. Okay. Now I'm going to show you something else. We need to know the number of terms for this formula. So the number of terms when you're given sigma notation, it is very easy to say it's the top term. And usually it is. When this starts at 1, it always is. But I'm going to generalize this. So the answer is 7. But I'm going to generalize it just in case that bottom number doesn't start out at 1. The way we want to do that is take the top number minus the bottom number and then add 1. So in this case, we take 7 minus 1 plus 1, and we get 7. That's a lot of work for just, why don't you just take the top number? Because maybe, just maybe, things might change a little bit for you, so you got to watch that. All right, plug and chug. Holy mackerel. I want you to practice this because I'm telling you this is the answer, I think. I hope I didn't make a mistake on that. just plug that in and practice and get those parentheses right. Don't do one thing at a time. You're better than that. You can plug it all in. All right, find a formula for the S sub n, the sum of the first n terms. So in this case, our answer will have an n in it. We want to end up with something that if I want to know the sum of the first 10 terms, I can just plug in 10 and get something. So just trust that the formula will do that for you. Okay, is it arithmetic or geometric? It looks geometric to me. Do we know the first term? Do we know the constant ratio? You bet. So the first term's 9. How do you get the R value? Remember, R value is any ratio of any two consecutive terms. So maybe you take 9, maybe you take, you take -3 over 9. That's awesome. That gives you -1/3. Or I could take 1 over -3. They both are going to equal -1/3. Okay. Boom. All you got to do now is plug that in. First term, constant ratio, and then you just leave n where it's at. This looks fine. You know, you're done really. But the 4/3, you can multiply the top and bottom by 3/4. Remember when they said by dividing a fraction, you're actually multiplying by the reciprocal? The reason is you pick the reciprocal, so this cancels this, so it ends up looking like you've moved the 4/3 into 3/4. So that's why 9 times 3 is 27, and I think they leave it their answer, 27 over 4, and then they leave this alone. You can't distribute that negative until you've taken it to the power. The power goes first, and then we subtract our final answer. So leave it. All right, I'm going to leave this in your notes. This is number 8. If you want to look at number 8, and I kind of walk through it. I get a lot of questions because it's just oddly worded a little bit. So there it is for you. Here's your first part of the assignment. We just did an assignment looks like this. We did an example that looks like this. So I just be careful about plugging and chugging. Yeah, I think it's pretty doable. There's number 8. Number 9's fun. This book says you should use technology and not use logarithms. I don't agree with that. So this is an example that's in the homework section. Sometimes they're like, oh, maybe we should show you an example before you give these problems. So here's one. We have the first term of 5. Great. We have common ratio 2. So far, so good. And here they tell you the sum is 635. So they're asking how many terms do we add up in order for that to happen. So it's just like anything. You fill in the things that you know and you solve for what you're looking for. So the sequence, they tell you this, they tell you that. We plug it in, we get this equation, and then we set that equation to 635. I have all the confidence in the world that you can solve for n. I would divide both sides by 5. I would add 1, and then I'd write it in logarithmic form. I think you can follow that. All right. I really miss not being with you in class because this is a fun thing to do for people. If you get somebody that you get them 20 feet, 20 meters, whatever, away from a wall, and then you ask them to go exactly halfway. So if this person goes exactly halfway, how far did they travel? Well, I'd say 10. Would you guys agree? So now they're there. I don't know if I can move this person. Whoa, I can. All right. So then I asked them to go go halfway of that. Okay. So halfway of this would be plus 5. And we maybe put it right there. So we've gone 10, and now we're going to go 5 Oh, let's go ahead and move them. And then maybe I ask them to go halfway again. So half of that is 2.5. So 2.5. So far, so good? Whoa. Oh, let's see. Oh, they're falling apart. They're falling apart. All right, you get it. So maybe I keep asking that person to take halfway, 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 halfway. And maybe you can see that we are going to get really close to that wall. Like super close. But can you always take a half of the distance? So back in the 1600s, there are two parties thinking about this problem, and one of them, Newton, decided, oh my gosh, let's just say he gets there. We've been here for 10 hours, going halfway, and they're really close to that brick or that stone wall. And Newton's like, you know what? I'm up to my limit with this. I've had it. I'm just going to say they've traveled the full distance. Okay. And then there's the other people like, no, he's not there yet. We need to keep going. Well, they're still there. 500 years later, 400 and whatever, 350 years later, they're still there. Newton went on to develop this thing called calculus because he thought about things as they approach something. Let's see what that limiting value is, and calculus was found. So why do I bring this up? Because look at those numbers. They represent a geometric sequence, but guess what? They don't stop. So the question is, if we add all these up, will I get a finite number? Can you add an infinite number of terms up? Well, look at this poor person. If they kept walking forever, they would pretty much cover that distance. So you could pretty much say that's about 20. And that's our goal, is can we add up an infinite number of geometric terms? Geometric because they have to get smaller as they go. If we add the same number every time, like in arithmetic, then we go on forever. There would be no limit. If we add a bigger and bigger number, like a geometric series that doubles every time, sure, there's some people who would rather send off, say go 2 miles and 4 miles and 8 miles, but can't do that. Come on, everybody's got a good story to tell. So, ladies and gentlemen, this is a beautiful thing. We take our sum of a geometric series and we think. As n becomes really, 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 really big, what happens to I do not want a u there. What happens to r to the n as n becomes large? When we say n becomes large, we say n goes to infinity. If you take 1/2 to a very, very large power and keep multiplying 1/2 times 1/2, what happens is that goes to 0. So what are we left with? We're just left with 1 minus 0. 1 times u sub 1 is that. No way. It's that simple, and it is. So look at our example. What was the distance that I went the first step? 10 over 1 minus, what was I multiplying each number by? 1/2. 10 divided by 1/2 is 20. So we would say if we add 10 plus 5 plus 2.5 and so forth on for an infinite number, we get 20. So ladies and gentlemen, our final equation for the section, there it is. Let's do a quick example. There it is. Do we have a first term? Check. Do we have a constant ratio? I hope so. We take 8 over 12 and get 2/3. You'll find that this will go very quickly. It's a much easier thing to plug in your calculator. 12 over 1 minus 2/3, 12 over 1/3, and you get 36. Cool. What if you're given a problem in sigma notation, and this is a good review for us. Well, first, look right here. That means we're doing an infinite geometric series, okay? So I immediately, if this is possible, I write this down. Okay? Do we have a first term? Don't jump and say it's 18. You can't do that. So u sub 1 happens when I equals 1. So plug 1 in. 18 times 2/3 to the first, and that's going to equal 12. R, the constant ratio, will always be the number that we're taking to a power. So in this case, 2/3. And yes, this is the exact same problem as what we just did. So we'll get 12 over 1 minus 2/3, and I believe we got 36. All right, I'm running out of time. I'm going to keep it under 20, and I've lied. I'm going to let you have number 9. I have written it out, and I'm hoping that you can follow because number 10 is the exact same problem. Good luck. I'll be there this is going to be a Wednesday or Thursday. No, it's going to be our Thursday, and so we'll certainly take some take some questions and so forth. Have a good one.